start. I'm going to go to full screen, and we should be off and running. Once again, if you cannot see a full screen slide that's titled Muscular System, please unmute and let me know. Muscular system, what is that next topic? We've talked about the physiology within the muscle itself, and to see that, we had to find the functional unit. It wasn't the muscle or the fascicle or the fiber or the myofibril within the fiber. It was that unit we call the sarcomere. Why do we pay so much attention to micro-dimensional units? It's because that's where the answer is. That's how a muscle contracts. A skeletal muscle has a sarcomere arrangement, and that arrangement is how a muscle can shorten with force. We've looked at that repeating process where myosin heads will bond, flex, release, and reset as a way of forming one cross bridge, consuming ATP in the process, and moving the end plate of the sarcomere toward the midline. But as we add it back up from sarcomere to myofibril, to fiber to fascicle to muscle, now we have to look at the system on the organismal level. When we look at that single organ that we call a muscle, and I want to emphasize that, if it's a muscular system, that's the organ system. The named organs of that system, like my favorite muscle, the biceps brachii, is an organ of that system. So what do we know from sarcomere physiology? First, muscles can only contract. That means they can only pull. Whatever their ends are attached to are going to get closer to each other. So how is it there are so many different bodily movements? I know, for example, the biceps brachii flexes the elbow, but it cannot extend the elbow. There has to be another muscle contracting to do that. So we're going to see this kind of opposite arrangement on both sides of the joint in order to get a motion like the elbow motion, which is back and forth. The secret is the variety of shapes and attachments that we find in our muscles. So we're going to be looking at the typical way we name and describe the organs of the muscle system. And let's start with their shape. Looking at this figure of my favorite muscle, the biceps brachii, we see the label tells us it is a parallel muscle. That's because there are basically two ends of attachment. They are basically in a straight line. They are always pulling in that straight line. If you think about it, here's a joint, and it's a hinge joint. It can only move like this. Can't move like this. So the muscles that are moving these two knuckles have to basically always be pulling in this direction. This flexor tendon, the muscle is actually back here. This flexor tendon will cause these two joints to flex when the muscle shortens. To extend the finger, I have to have an extensor muscle on the other side. It turns out it's back here, and extends the finger back out. Each muscle has this red or pink portion, which is called the belly or body of the muscle. That's the fascicle, fiber, and myofibril part, the contractile tissue. Up at the end of the figure, I hope you'll notice here and here that there are whitish regions. This is where the muscle fibers are blending into and attached to collagen connective tissue. This collagen tissue forms what's called the tendon. The tendon is the connective tissue that hooks a muscle to the skeletal element, the bone. So muscle to bone, tendon. You recall that bone to bone we call ligament. Now this parallel muscle, all of these fibers are basically going to be pulling in a straight line, parallel to one another. If it's a large muscle by the biceps brachii, as you add fiber after fiber after fiber, it will bulge out in the center like you see here. But in fact, in general, it's still pulling around a hinge joint, the elbow, and producing this flex motion. That, if you cut across it, you can see the fascicle within the muscle arrangement, and within the fascicles, you can just barely see the fibers within the fascicle. If we magnify that, those individual fibers will show myofibrils at the highest level of magnification. So here we are, a parallel muscle pulls in a straight line. You'll notice something, though. If you tried to arrange a number of parallel muscles in a small space, they'd basically be interfering with one another. So we're going to try to address that later with a different shape. Here is a convergent muscle. It is a fan shape, and this is the pectoralis major, a muscle of the thoracic region on each side of the sternum. The one region, one area on the left side is the base of the muscle. In attachment, we call that the origin. The attachment starts here on the clavicle, goes down the sternum quite a ways, and actually curves around across a couple of rib and costal cartilage regions. That broad attachment means that it can actually pull over an array of angles. So the top part is actually pointing down toward the attachment here on the humerus. I'll get to that in a second. So these strands up here would be most important when you're flexing the humerus in this direction with an upward motion. If you're flexing with a downward motion, so your job is to push like this, downward, that's where the bottom region, the inferior region down here, would have the most effect. You'll notice in cross-section, you still see that arrangement of fascicles and fibers. It's a flat muscle, front to back, but its big feature is it can pull directly on the tendon from a variety of angles. So it can be appropriate for a very mobile joint. This is a ball and socket joint. It doesn't just move in one plane when it flexes. It can move up, down, or straight forward. This is that accommodation to space. When we're moving the elbow, when we flex the elbow, that's a power move because we're moving the entire forearm and hand. So having one muscle here, the space is available. But what about this? When we're flexing all of these different joints, look at this. I can flex my wrist. I can flex my palm. I can flex my phalanges. Every one of these flexor joints has to be served to, in order to flex this finger separate from this finger, I have to have a different muscle attached. This is where these smaller muscles, called unipennate muscles, come in handy. You'll notice that the straight up and down orientation of the tendon shows you the direction it's going to pull. From the NATE of unipennate, it would pull it straight up. But you'll notice that the body of the muscle is offset and it's at an angle. That allows you to spread out the attachments of smaller muscles in a very, very concise area. So here, where I'm going to arrange the flexor muscles for my hand, my palm, and my wrist, I can pack these small flexors close together and basically use unipennate muscles to displace their attachment and still find room on the radius and ulna in order to have the origin in. Unipennate is an offset kind of design, pulling in an angle. In other places, there are massive muscles like the rectus femoris. Rectus means straight, and femoris means femur, and it is this muscle, I can't show you very well, right on the front of the thigh, right above the kneecap. In fact, that lower tendon area is going to suspend the patella over the knee and cross the knee to attach to the tibial tuberosity. The central tendon runs from that white area right up that central line, but you'll notice the angles of the body of the muscle, the contractile units. They're going to pull at an angle, but because of the connective tissue in this bipinnate or double feather condition, it's going to basically elevate that lower tendon area. This muscle will extend the knee, so it's important in walking, more important in running, because as hard and as fast as you can push with your propelling muscles on the back of your leg, you can't really run faster than you can put your other foot in front to catch yourself. And so that's why the rectus femoris is one of 4 muscles that form what's called the quadriceps group. Finally, not quite finally, the multipinnate muscle just extends this idea, and the deltoid is a great example. It is a muscle that's here, extending over the lateral edge of the shoulder and attaching, that tendon that you see, attaching right down here on what's called the deltoid tuberosity of the humerus. That principal action is to abduct the shoulder, not the drop, but adduct. Anytime you're lifting your humerus from the anatomical position, the deltoid works in some way. Its attachment, you'll notice, is sort of a big U shape at the top. It's going to start here at the clavicle, run down over the acromion, and back along the spine of the scapula. So if you took that muscle and tipped it up, the attachment at the origin would look about like this. Now, this is an interesting muscle because it is a muscle that will always work in abducting, but you'll notice I can abduct forward combined with flex, abduct laterally. I can even abduct posteriorly. That means that when I abduct in an anterior position, so I'm using the pectoralis major for the flex part, but also assisting with this forward packet of the deltoid. That means that this packet can be contracting and the top packet can be contracting, but the posterior packet has to be relaxed and stretching in order to allow that motion. This is one named muscle that is controlled by separate nerves, 1, 2, 3, to correspond to the anterior, central, and posterior packet. In order to work this one muscle, you have to have multiple nerve connections. This is going to be something we see repeated in large muscles, like the trapezius, where within one muscle, its attachments allow what are actually opposing motion. Finally, here's an unusual muscle because although it's kind of packed down in the back to the skeletal system, that's just kind of to hold it in place. The contractile units form a circle, so it's called a circular muscle. Circular muscle is soft tissue all the way around, and when it contracts, it closes a hole. That means that in closing that hole, sort of like the drawstring on a pair of sweatpants, it tightens it down smaller. This is an example of this is the orbicularis oris muscle. It is a circular muscle that is in the soft tissue around the mouth. Now, I want to point out, it's not right here in the tip of the lip. The lips are toward the opening. The orbicularis oris is a circle behind that. So when you contract it at maximum force, it produces that kissy mouth or that fish mouth, pushes those soft lip tissues, which are not contractile, out forward of them, and basically closes the mouth very tightly. So we are able to control the opening of our mouth and the opening of other places. There is an orbicularis oculi muscle that does the same thing, closing down the eye opening. So those are the basic shapes we see in skeletal muscles. We also have a science called biomechanics, It basically takes the lessons of general science, that of, in this case, levers and loads and fulcrum, and applies it to the body. This is a good example of how mechanics, the physical properties of the universe, things like mass and leverage, can be applied and must always be observed within the body. This is an example, and don't worry too much about the definitions and these particular joints. I just want you to see that you can get three kinds of levers by putting each of those three things in the middle. So the first class lever puts the fulcrum in the middle. This is sort of like a teeter-totter. Load on one end is pushing down, and to move that load up, you have to pull down or apply the force on the other end of the lever. And basically it pivots around the fulcrum. This drawing shows you an example of something that's really automatic to us. We have a head that is mounted. The fulcrum would be the top of the cervical vertebra, that axis, and the occipital lobe of the skull that rests upon it. Now, that's well behind the center of gravity. There's a lot of weight out here in front of the fulcrum. In fact, try this. It's normal for us to hold our heads up, to look straight forward, to hold our heads level like the anatomical position. But if you consciously relax that muscle, your chin drops to your chest automatically. You're not pulling it down. Gravity's moving it because of the distribution of the load well forward of the center of gravity. So we have a muscle that's attached back here along the scapula and the spine that is attached to the back of the occipital lobe behind the fulcrum. And by contracting that muscle, it draws our head up to a level position and presents our eye and face to the world in front of us. A first-class lever. Second-class lever, you'll notice now the load is in the middle. This is sort of like a wheelbarrow. The fulcrum would be the wheel, the load would be in the bucket, and you'd pull up on the handles in order to move it. Now, this move, I'm going to be standing right now in the anatomical position. So just take my enthusiasm from the expression on my face. I'm going to shift the balance from my heels. So I'm lifting my heels slightly off of the ground, putting the weight on the ball of my foot. That's where the fulcrum is. The load is my body weight, which right now the weight is pressing down through the skeletal system, through the ankle, and the metacarpals of that arch, holding my heel slightly off the ground. Now, behind that load, we have the muscle called the gastrocnemius. It is a muscle that is that bipennate muscle that spans from the lower region of the femur, you can see on the right there, back to the calcaneus. So when I pull the applied force, it basically raises me up on tiptoe. So as I elevate, I'm using a second-class lever in the gastrocnemius. Now, that second-class lever isn't just for standing on tiptoes. When I take a step, I plant my heel and I basically rock forward to the ball of my foot. At the end of my stride, my other foot is off the ground swinging forward, and this gastrocnemius contracts and flexes my foot, pushing me forward and giving me another 8 to 12 inches of stride length. So it's a very, very practical muscle. The third-class lever has the force in the center. This is my favorite muscle, the biceps brachii. You can see why it's called biceps. It splits at the upper end into two heads, and you'll notice its connection is not to the humerus. There are two connections on the scapula, which we'll name in our exercise next week. But it's basically a parallel muscle pulling to that single connection on the radius. So this is an example where the fulcrum is the humerus to ulnar joint, a hinge joint, and the load will be your entire arm and hand and whatever you have in it. If you can imagine a barbell in this hand, that could be a big load. So when I attach the muscle here, the applied force, I basically am pivoting the fulcrum to produce a flexing movement. In this case, a third-class lever and the biceps brachii. Those three mechanical explanations are going to be just a connection to the general science, the not necessarily living science, but the rules of mass and movement, of leverage and gravity that apply to our skeleton and muscles and our movement every day. Critical terms will be introduced on Monday. We'll continue with this as we think about how to describe a muscle. Every muscle has its attachment points. So because the biceps brachii is where it is and attached to it is, that when I flex the elbow, you notice there's one end that does not move and one end that does. The attachment end, which does not move, is the origin. To move when you're contracting, you have to pull against something. You pull against the origin end. In this case, the origin of the biceps brachii are two attachments, one to the top of the glenoid cavity and the other head attaching to the coracoid process of the scapula, the origin end. When we flex this muscle, the principal action, flex the elbow, we notice that this end does move. This is the radial tuberosity of the radius, and it is we are basically controlling this in a complex way from our nervous system as a movement we have learned as we were learning to control our body. And so the insertion end, the mobile end, is producing movement at that joint. Now, when I flex, there is a muscle that's attached right below the bicep brachii called the brachialis. It can actually, if I put a real heavy load in my hand, and so my biceps is pulling very hard, the brachialis can actually help flex the elbow. That makes it a synergist for flex. So for flexing the elbow, we would say the prime mover, sometimes we call it the agonist, is the biceps brachii, and it has synergistic action from the brachialis. When I flex my elbow, the muscle that goes around the back, the one that's main job is to extend the elbow, has to be relaxed and stretched. That makes that an antagonist for elbow flexion. That muscle is the triceps brachii. So we have a set of conditions in order to understand the attachment and the movement of each muscle in the body. And that's where we'll start next week. Now, there are 4 figures here that show what are called the superficial muscles. Muscles are laid down in layers, and those layers are shown in this 4-part slide presentation and named, as the superficial muscles. So I'd like you to take a hard look at this, and especially the lab assignment, pick out those 12 muscles that we will be required to complete and understand complete properties for. So I'm ready now to end the show, stop the recording.